Hello, and welcome to the training for the Mill Creek Alliance Water Quality Monitoring Program. We're so glad you're joining us this season. If you're a new volunteer, there'll be a lot of new information here. For existing volunteers, this should be an easy reminder. On today's agenda, we will begin by introducing our organization, the Mill Creek Alliance. Then we'll dig into the Water Quality Monitoring Program specifically, as in why we monitor, where, how, and for what parameters. Then we'll review the roles of samplers and lab analysts and discuss safety considerations for all participants. Our mission at Mill Creek, at the Mill Creek Alliance, is to champion the resurgence of the Mill Creek watershed as a natural and community asset. We envision the watershed as a healthy ecosystem where people and communities can thrive. The organization has been around in some form since 1994, and our focus is on restoration, education, and recreation. We are a small but mighty nonprofit staffed by a handful of employees and an army of volunteers and interns. We encourage you to visit our website to learn more information about each of our staff members, the history of the Mill Creek, and all the ways that you can get involved with our organization. So, moving on to why we monitor. Water quality is at the heart of everything that we do, and the data that we generate through the Water Quality Monitoring Program supplements the data used by organizations like the Ohio Environmental Protection Agency, the Ohio Department of Natural Resources, the Metropolitan Sewer District, Butler County Water and Sewer, and the Midwest Biodiversity Institute. Independent and community-driven water quality monitoring allows us to advocate for stream health, catch and respond to issues faster than other agencies may be able to, educate watershed stakeholders about environmental and economic benefits achieved by projects and policies, and to foster connections to the waterway and ownership for its success. A little bit about the Water Quality Monitoring Program. Beginning in 2013, the Mill Creek Alliance Water Quality Monitoring Program has grown to over 100 dedicated volunteers, assisting with streamside sample collection at 57 sampling locations and laboratory analysis of 9 different water quality parameters. In coordination with other local monitoring programs, we sample on the second Saturday of every month from March through November. This collaboration allows our data to be comparable with that collected on the Great Miami River through Rivers Unlimited and the Little Miami River through the Saturday Stream Snapshots program. Collectively, we can generate a holistic view of water quality in our streams throughout the Southwest Ohio region. Our Mill Creek Alliance Water Quality Program data is made available on our website and is also presented at the annual State of the Mill Creek Address each year in February. So what do we test for and why? Each of the 9 parameters we test for plays a critical role in the health of our water, and collectively they tell us an overall story of water quality and stream health in the Mill Creek. Phosphate and nitrate occur naturally in the environmental waters and are essential to aquatic life. However, when their levels increase due to man-made activity, the effects can be detrimental to stream health. Conductivity, which is an indirect measure of total dissolved salts, is a useful measure of water quality. Each water body tends to have a relatively constant range of conductivity that, once established, can be used as a baseline for comparison with regular conductivity measurements. Significant changes in conductivity could then be an indicator that a discharge or some other source of pollution has entered the waterway. Turbidity is an indicator of the clarity of our water, which can be an indication of erosion and increases with discharge and runoff from impervious surfaces. Increased turbidity can increase water temperature, reduce dissolved oxygen, and impact plant growth, all of which are important for aquatic life. The amount of plant matter and algae in the waterway is measured as in vivo chlorophyll A. This metric can be influenced by nutrients such as nitrogen and phosphorus, as well as turbidity. Increased chlorophyll tends to increase pH, which is a measure of how acidic or basic the water is. The U.S. EPA water quality criteria for pH in freshwater suggest a range of 6.5 to 9. Fluctuating or sustained pH outside of this range indicates physiological stresses to many aquatic species, which can lead to reduced biological diversity in streams. Coliform bacteria, and specifically E. coli, are normally found in the digestive tracts of animals, including ourselves, and can be released through our waste. When coliforms contaminate the environment in large numbers, they present a health hazard for recreational use of the waterway. Optical brighteners are the chemicals in your laundry detergent that make your whites whiter and your brights brighter. They are not harmful in and of themselves and are effectively removed by wastewater treatment plants, but the fact that we can find them in our water samples serves as indicators that untreated wastewater has entered the stream. The last parameter measured is temperature, which is recorded by samplers in the field for both air and water temperature during sample collection. Water temperature influences and is influenced by many other parameters, so it is important to have it in our dataset. Let's switch our focus to the roles of the lab volunteers who pick up where the samplers leave off. Lab analysis occurs on sampling Saturdays between 10:30 a.m. and approximately 3 o'clock p.m., or however long it takes to complete the work. Analysts are welcome to arrive as early as 10 a.m., as some samplers tend to drop off their samples early. There are 7 different workstations in the lab. Some of them operate better with 2 or even 3 volunteers. For that reason, we prefer to have 8 to 10 volunteers for every Saturday event. Analysts are required to indicate their intention to work on the lab volunteer availability document available on our website so that lab staff can plan for the day. Because the coliform tests need to incubate for 24 hours before they are counted, 2 or 3 volunteers are required each Sunday of the event weekend. These volunteers read and record the results of the coliform tests, which takes about 2 hours. While lab experience is helpful for any of these activities, it is not mandatory. Analysts have access to lab training materials on the website, and the standard operating procedures are in the lab along with on-site training. Much like the samplers in the field, analysts are expected to make safety their #1 priority. So, let me ask you, who is the person most responsible for your safety? You are! All analysts will be given a safety tour of the lab so that they know where all of their personal protective equipment, first aid equipment, and the right to know station is located. Volunteers are expected to wear gloves, goggles, and masks provided. When working with the water samples, please remember that the sample is still king. Treat the samples the same as in the lab as was done in the field. As in, take care not to contaminate the samples. Do not touch the insides of the bottle or the undersides of the lids. Remember, water only comes out of the sample bottle. Water is never poured back into the sample bottle. When using pipettes, use a new clean pipette tip for every sample. Water samples for most tests will come from the large bottles. The small sample bottles are for coliform testing only. Lab work can be very technical. Always ask for help if you need it. If a data result doesn't look right to you, it's probably not. As with samplers in the field collecting good water samples, when in doubt, dump it out and perform a new test. When all of the testing is complete, all samples and spent chemicals should be poured down the lab drain. Please tune in to the following videos from Rivers Unlimited, Adgene, and Eppendorf, as well as videos made by MCA in the past for demonstration of the lab sampling procedures. When in doubt, refer to the lab copies of the standard operating procedures and don't hesitate to ask questions.
Thank you for volunteering with the Lower Great Miami River Water Quality Lab. I'm Sarah Meadows, Public Involvement Coordinator with the Hamilton County Soil and Water Conservation District, coming to you from the Great Miami River. We work closely with Rivers Unlimited to get this lab certified as Level 2 through the Credible Data Program. This means our data from the lab can be used at the state level by Ohio EPA, the county level by the Soil and Water Conservation District, by local nonprofits such as Rivers Unlimited, and others. This data can be used for regulatory purposes to identify red flags that help prioritize projects and other watershed planning purposes. For this reason, it's important that you follow the procedures outlined in this video. For example, every 10th sample will be a duplicate to ensure there are no errors along the way. If this is confusing, don't worry. There will be at least 2 lab managers on site during every sampling day. Mike Miller is the program manager, Lisa Lee is the lab manager, and Bernie Moeller is the quality control officer. Thanks for watching. Enjoy your video.
Hi, I'm Adam at Hamilton County Soil and Water Conservation District, and this is the total phosphorus analysis station.
Major sources of elevated phosphorus levels in our local waterways include treated effluent from wastewater treatment plants, as well as untreated discharges from sewer overflows and home septic systems that aren't functioning properly. Other important sources include fertilizers applied to agricultural fields and lawns, and the sediment resulting from excessive streambank erosion and earth-disturbing activities such as site development. While phosphorus is an essential element of life, its presence in excess in our creeks and rivers can lead to harmful algal blooms and/or dissolved oxygen levels below that required by many species of local aquatic wildlife.
So when you come into the lab, our equipment will be set up a little bit like this. So let's have a quick introduction to what we have here. So this is our Hawk Method 8190 kit, and everything that we do is based on this. So it all comes out of this box here, and the box includes a couple of powder packets, a couple of bottles. One's deionized water, the other is a buffer solution, and some test tubes. So each test tube comes with a little bit of acid already in the bottom. So there should be some liquid in it when you pull it out of the box. Some of the other equipment we have here, this is our sample bottle that a volunteer has brought us from a local stream. Just a bottle of deionized water to rinse things off with. These are pipettes, and we'll demonstrate how to use these in a little bit, but these are for drawing up samples and solutions and squirting them into the tube. This is an incubator, which is perhaps just a fancy name for a heater, right? We've got some chem wipes here. We've got a photospectrometer here, which is going to measure the amount of phosphorus in each tube, and just a laptop with an Excel spreadsheet where we're going to record the data. When you come into the lab, if any of these things seem to be missing or out of place, or you have any questions at all, just ask one of the lab managers. Now let's take a closer look at the process. So we run our phosphorus analysis in batches of 25. So we have 25 tubes per rack, and the reason for that is simply because there's 25 slots in our incubator. So we start off at the beginning of each batch by getting 25 tubes in the rack, and then we'll just one by one bring in the sample and start squirting them into the tubes. Now it's important to remember to set up your duplicates and your spikes as you do the rack. So we're going to have a duplicate and a spike. We have to have it for 10% of our sample. So we'll have one on the first sample, and then every 10 samples after that. So we'll have one on the 10th sample, and the 20th sample, and the 30th sample, and so on. So when we get our first sample and we write sample 1 on it to correspond with the number on the sample bottle that it brings us, we're going to put 5 milliliters of sample into that. So we note that we have 3 different pipettes here. One is for 5 milliliters. So we're going to take 5 milliliters of sample, put it in the first. Now directly after 1, we're going to have 1 dupe, and we signify that by just putting a dot after it. So we have 1 dot written on the lid here. And so there's no need to change your pipette tip from this one, since it's coming out of the same sample. But do make sure to put the lid back on your sample between them and shake them up so that we get a good mixed sample for each tube. So for the second duplicate sample, we're going to do 5 more milliliters of sample into that tube. And then on the third tube, this is our spike. Again, we're drawing sample out of the bottle here and putting it in. But this time, we only want 4 milliliters of sample. So we have a different pipette for this that's calibrated to 4 milliliters. So again, because this is the same sample, we can just use the same pipette tip. So we'll take it off the 5 milliliter pipetter and put it on the 4 milliliter pipetter. And we can then transfer the sample into the third tube. And after we get those 3 out of the way, then we can move on to sample 2, sample 3, sample 4, and just keep going in order until we get to 10. And then we need to remember to do our duplicates and our spikes. So the method we're going to be following is Hach's total phosphorus method 8190. And it comes in this kit here, like I mentioned. And just to show how simple this is, we're simply following a few steps with pictures. And so we'll have the pictures on the screen to guide you through the process through the rest of the video. But to take a closer look inside the Hach kit, we have 2 different types of powder. And it's really important to read what we have here because they look exactly alike, right? We have a potassium persulfate and one says phosphate reagent. And so it's important to be using the right one at the right time. Also note that there's 2 different bottles in there. There's the sodium hydroxide buffer, and then one's just a DI water. And we won't be using that. In the lab, we'll usually have bottles of DI available for you to use. So under the hood, how this really works is pretty simple. We have various types of phosphorus that might be locked up in the water in organic and inorganic forms. And so we want to get this all into one form that we can measure with our machine here. And so the idea is that we're going to digest the phosphorus in this water so that it's all in inorganic forms. And so we've got a little acid in the bottom of the vial. We're going to put in the sample, we're going to add the potassium persulfate, and then we're going to heat it up, right? So the acid plus the persulfate plus heating it up is going to digest it, and then we'll have all of our phosphorus in one form that can be easily measured. So the first steps are going to be to turn on our equipment. So we're going to start up our incubator. We're going to start up our photospectrometer, and we're going to fire up our laptop. Okay, now we're going to pipette some water sample into a tube. So let's remove the cap on our first sample tube. Remove the cap on our sample. Oh, very important. I almost forgot. I'm glad I did, because it's very important that we shake these samples up every time we draw some. There's lots of phosphorus bound to the fine sediment in here, and so we want to measure it all. So let's shake it vigorously every time before we draw a sample. Now, before we grab a pipette tip out of the bag and we take our DI sample and we just spray the outside of it off and inside as well. Now, in addition to spraying it off, we're also going to pull and then throw away 3 pipette loads of sample before we load the sample into the tube. You want to get a nice firm fit here, and on a pipette, you move it down and then you let it back up slowly to draw the sample back in there. So you're sucking it back in. And then when you want to spit it out, you push it back down again, and then you can push it back down a little bit extra. You can feel a little click there. And that helps to blow out, any extra droplets that are sitting in the bottom of the pipette tip. So push it down until I meet that resistance. Draw it up slowly and smoothly. Then I waste it out and extra push. And I'll do that 2 more times. And now I can draw my sample. And there you go. And next we're going to add our potassium persulfate powder packet. And the first thing you want to do is you want to hold it right side up and give it a few good flicks and get all that powder down to the bottom of the packet. Now the packet has a little blue line that says tear here. I recommend cutting a little bit below that. Sometimes you don't. It might not. It might not open if you don't cut a little bit below that. So you cut the top off. You kind of crease it open like that, and you just pour it in the tube. I like to hold it over a garbage can for this. And you shouldn't have trouble getting most of it out. We don't need to work for 10 minutes to get every last granule out of here. That kind of level of error is built into the method. So now we're going to put the lid back on, and we're going to shake it to mix up the powder, and we're going to do that until the powder is completely dissolved. It shouldn't take too long for this one. And that's looking pretty good. So once we have our potassium persulfate in, it's ready to get cooked in the digester for 30 minutes at 150 degrees Celsius. So we put it in and we press start. And now we wait for 30 minutes. Once the timer on our digester's gone off, we're ready to pull these samples out. Now the samples are going to be a little bit hot, right? So you can have gloves to pull them out and protect your hands. I find that if I just pull them out pretty quickly, it doesn't. I don't burn myself. So, but we do want to cool the vials or the tubes off before we work with them any further. And so we fill this tub up with water and just give it a little bath, just until it's cool enough to handle. So once your tubes have cooled down enough to handle them, we can go ahead and add our sodium hydroxide buffer. So recall that when we pulled our tubes out of the hot kit, they had a little bit of acid in the bottom. And so that was there to help digest the phosphorus when we added the persulfate and heated it. But now that process is over. So we're going to add this basic solution to help bring the pH back up to a more neutral level. So we're going to pick a different pipetter this time. This one is set to 2 milliliters as opposed to 5 milliliters that we used to draw the sample. So we'll take our bottle here. Remove the lid from our test tube. And we can draw up a practice run just to get the inside of the pipette tip wet, and we can spit it right back down into the bottle. And then draw our final one. And dispense it into the tube. Now we're going to invert this thing 3 times to mix it. Now at this point, some of our samples are going to get pre-read using the photospectrometer, and some of our samples aren't. And so the way that we do it is if the turbidity of the sample is greater than 50 NTU, then we're going to do a pre-read. And so you'll simply walk over to our friends at the turbidity station and ask them what the turbidity measurement was for that sample. But we'll pretend that this one was above 50. So now that we've shaken it up, we're ready to do a pre-read. And so we come over here to the photospectrometer, we open it up, and we simply stick it down into the hole and press read. But it's really important because this thing is measuring how blue, basically, the solution is, because our next reagent is going to turn the phosphorus blue. So any fingerprints on the tube can interfere with those measurements. So we're going to just wipe this off real good with a Kin wipe before we start. Insert and press read. And once we get our measurement, we just come over here and enter that into the appropriate location on our spreadsheet. And now that we've pre-read to correct for any effect that the turbidity of the sample might have on our photospectrometer reading, we can go to the final step where we add our phosphate reagent, which is going to turn all the phosphorus blue in the tube so that we can get a final measurement of how much phosphorus is in the sample. So, just like the potassium persulfate, we're gonna take the packet, we're gonna flick it to get all the powder to the bottom. We're gonna cut it just below that blue line. Probably should have pulled the cap off the tube first. Then just squeeze the packet open and pour it in. Now the reagent is going to take quite a bit more shaking to get it to dissolve than the potassium persulfate did. So we're going to follow what the method tells us to do, and that is to invert it 20 to 30 times. So I always do 25 just to split the difference there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Now, once you've shaken your test tube 25 times, we need to set a timer for 2 minutes. So you can't take your measurement until 2 minutes have passed, but you need to take your measurement within 8 minutes after you're done shaking. Just because that's the time frame where the chemical reaction is optimal for getting an accurate reading of the amount of phosphorus in the sample. So we'll put this aside, we'll wait for 2 minutes, and then we'll put it in the photospectrometer. And now that 2 minutes has passed, the moment we've all been waiting for, let's measure how much phosphorus is in this tube. Don't forget to wipe your fingerprints off the tube. Insert it and press read. All right, we have our reading. And now we simply go to the correct location on the spreadsheet. Enter the reading, and we're done. Always press save. And now that we've finished measuring the phosphorus in the tube, we want to make sure that we dispose of the liquid inside correctly, because there are some chemicals in here that could be hazardous to the environment. So make sure to pour the liquid into a container that can be properly disposed of, and then we'll just throw the tube into the garbage.
Hi again! Hopefully by now you're getting excited for the sampling season to start. Remember, we sample on second Saturdays from March through November. Samples collected should be turned into the lab no later than 11 a.m. Volunteers for processing should arrive around 10. If for some reason you can't come in or collect your samples, please contact Lisa Link and we'll find a substitute for you. Thanks again, and we look forward to a great sampling season.
Hello, and welcome to the training video for the Mill Creek Alliance Water Quality Monitoring Program's Nitrate Nitrogen Testing Station. Nitrate nitrogen is a nutrient that is natural to aquatic ecosystems. However, surplus amounts of nitrate nitrogen can enter the water from human and animal waste, decomposing organic matter, and fertilizer runoff. This can lead to increased plant growth and eutrophication. High levels of nitrate nitrogen can also interfere with growth development in fish. The nitrate nitrogen testing station involves the use of chemicals. You should wear the gloves and safety goggles provided for your protection. Should an emergency arise involving the use of these chemicals, please refer to the Right to Know station in the laboratory. On sampling Saturdays, field volunteers will collect samples from our sites and deliver them to the lab for analysis. These samples should be available for you to use when you arrive on site. When you arrive at the nitrate nitrogen station, the following materials should be available for use. If anything is missing, notify laboratory staff. Equipment: Hach DR3900 spectrophotometer, nitrate standard solutions in 0.5, 1, 2, 5, and 10 milligrams per liter, 1000 microliter pipette, 200 microliter pipette, 500 milliliter wash bottle, white plastic test tube racks, waste container, a fine tip Sharpie and pencil, safety goggles, and the nitrate nitrogen SOP. In addition, you should have the following supplies: Hach Nitrates TNT Plus 835 cuvette tubes, nitrate TNT Plus reagent, 50 to 1000 microliter pipette tips, 2 to 200 microliter pipette tips, DI water, Kim wipes, nitrile gloves, and the nitrate nitrogen lab data sheet. Review the SOP provided before you begin and refer to it while working as needed. If you have any questions, contact laboratory staff. Begin by writing your name and the testing date at the top of the lab data sheet. With the testing chamber lid closed, power on the spectrophotometer. The meter will complete a self-check, then go to the main menu. Press the Barcode Programs button on the main menu. This test is fully automated. From this point forward, once you insert the test tube into the meter will do everything else for you. You do not need to zero the meter. Label test tubes for all the samples you are going to run with the marker provided. Note that some site numbers on your datasheet may be missing if a site has been retired or changed, so mark tubes carefully. You will be running samples for a before testing standard series, each of our sampling sites, 5 field duplicates, 5 laboratory duplicates, and an after testing standard series. As this test is time sensitive, you should prepare samples in small batches that you can comfortably manage. 10 samples per batch is recommended. Your first batch should always include the before testing standard series, and your last batch should always include the after testing standard series. Stream water samples used for this test come from the larger 250 milliliter sample bottle. Bottles are kept organized in the main lab area. All lab volunteers share usage of these bottles, so you can pick up a small batch of bottles to work with, then return them and get another set. You will not necessarily be processing the samples in chronological order. For each sample, complete the following testing routine. Shake the sample vigorously to make the sample homogeneous. Place a new, clean 50 to 1000 microliter pipette tip on the 1000 microliter pipette. 1000 microliters equals 1 milliliter. Using proper pipetting technique, withdraw 1 milliliter of sample from the sample bottle and waste it into the waste container. This is done as a quality assurance measure. Then, withdraw another 1 milliliter sample from the sample bottle and dispense it into your appropriately labeled test tube. Next, place a new, clean 2 to 200 microliter pipette tip on the 200 microliter pipette. 200 microliters equals 0.2 milliliters. Using proper pipetting technique, withdraw 0.2 milliliters of nitrate TNT plus reagent and dispense it into your test tube. Cap the test tube securely so it does not leak, shake to mix, and replace it into the test tube rack. Take care when handling the test tubes at this point, as they will become hot to the touch. Start a 15-minute timer. You may use the timer on the Hawk machine or your own personal timer. Once the 15-minute reaction time is complete, you will continue to process each sample as follows. Use a Kim wipe to remove fingerprints or other impurities from the outside of the test tube, then insert the test tube into the meter. The meter will generate a reading. Enter this reading in the corresponding space on your lab data sheet. Remove the test tube from the meter, then reinsert it to generate a second reading. Enter this reading in the corresponding space on your lab data sheet. Move the completed test tube/sample to a predetermined finished area in your test tube rack. Continue this process with all the samples in your batch. Process the next batch using the same testing routine until all samples are completed. Please note, beyond the 15-minute reaction time, sample color may overdevelop and lead to inaccurately high readings. For this reason, samples must be read as soon as possible after the 15-minute reaction time is complete. Run small batches of samples for this reason. Do not attempt to run more than 15 samples per batch. Once all testing is completed, clean up the station as directed by the SOP.
for bringing it away. Ooh. Quality assurance, right?
After incubation, mark each yellow well with a permanent marker, including the large overflow well. To determine the number of total coliforms, count the yellow wells that are equal to or greater than the comparator, and then refer to the MPN table included with the quantitrays. The most probable number of total coliforms for this example is 17.8 per 100 ml. If using quantitray 2000, count the overflow well as a large well. To determine the number of E. coli, view the quantitray with a UV lamp in a dark environment, shining the light away from your eyes. Keep the light within 5 inches of the tray. Count the fluorescent wells that are equal to or greater than the comparator, and then refer to the MPN table. The most probable number of E. coli for this example is 8.7 per 100 ml. If you're unsure whether a result is positive, incubate the sample up to an additional 4 hours, 28 hours total, to allow the color and/or the fluorescence to intensify. Please follow these testing guidelines. Store tests at 2 to 30 degrees centigrade, away from light. Use only sterile, non-buffered, oxidant-free water for sample dilutions. Because these procedures may not reflect your local regulations, for compliance testing, be sure to follow all local regulatory procedures. Remember these tips. If a water sample has some background color, compare the inoculated ColAlert sample to a control blank of the same water sample. Always follow aseptic technique when using ColAlert and dispose of all samples and materials in accordance with local regulatory guidelines. If you have questions or need more information, call the IDEX water microbiology experts at the number on your screen.
Welcome to the pipetting tutorial how to pipette correctly. I'm using a 2-button pipette. It has a control button with 2 stops and an ejector button. Pipetting starts when you attach the tip. Apply light pressure to insert the pipette into the tip. There is no need for force or moving from side to side. This would only strain your arm and damage the pipette. When aspirating liquid, 2 factors influence accurate liquid uptake: the aspiration angle and the immersion depth. The aspiration angle should be vertical. Otherwise, too much liquid is aspirated. The immersion depth, meaning the depth of the pipette tip inside the liquid, should be as large as necessary but as small as possible. If the tip is immersed too deeply, additional liquid can be easily aspirated due to the capillary effect. Press the control button down to the first stop and immerse the tip into the liquid. Once the aspiration angle and immersion depth have been checked, slowly release the control button. Press the control button down to the first stop again and aspirate once more. Repeat this 2 to 3 times to saturate the air in the tip. When dispensing liquid, the angle of the pipette should be between 20 and 45 degrees, whilst the tip should stay in contact with the vessel wall. This guarantees optimal flow out of the liquid into the target vessel. Press the control button down to the first stop. Then perform the blowout by pressing further down to the second stop. This ensures that the tip is emptied completely. The last step during pipetting is ejection of the tip into a garbage bin by pressing the ejector button. Achieve accurate and reliable pipetting results with soft tip attachment, vertical aspiration, a low immersion depth, and a 20 to 45 degree dispensing angle directly in contact with the vessel wall. So, improve your pipetting skills.
Please remember that this and all other trainings are always available on our website, themillcreekalliance.org. In addition to the training materials, you can get copies of important forms, directions for the day of sampling operations, access to the lab volunteer availability schedule, and more. To access this, go to the water quality portion of the website, click Current Volunteers, and log in with the password Saturdays. Thank you so much for your time today. If you have any questions, comments, concerns, or even just a good joke, you can email the program coordinator at any time. Thanks again, and have a great year.